but it's okay to see that there is a reasonable number of people who have joined. So usually when I'm displaying my screen sharing, sometimes disturbs. So I hope that this time it is showing, and also that my audio is clear enough. I am working from the university, and the network usually is not that stable when I'm there. But I hope the link is clear from my side, and there are no interruptions on your side, and also that the slides are showing on your side. Okay, so if the slides are showing on your side, then it means everything is okay. So today we shall be looking at the last topic. The other group has really finished this topic. I think their time schedule was not that much affected like yours. I think yours was affected by the Christmas break, and also some of the tests that were happening on the weekend. However, I think you're still in a good position, and maybe you'll be fresher from these ideas since you're doing a test this week and an exam next week. So, so this topic is evolutionary computation. It is a topic in which we shall look at what is referred to as the field of evolutionary computation, and more specifically at one of the methods under evolutionary computation referred to as genetic algorithms. So this will be the focus of this topic. So this topic is coming from one of the reference texts that I gave you of Artificial Intelligence, A Guide to Intelligent Systems by Michael Negnevitzky. And it is chapter 7 in the book. However, the content that we have in the slides are also coming from that book prepared by the author of the book. So what we see here is the outline of the topics of the subsections we are going to cover in this topic. Of course, usually starting with an introduction, where we shall discuss evolution. And then after that, we shall see whether we can simulate natural evolution. After these two, then we shall move on to one of the methods that is under evolutionary computation referred to as genetic algorithms. And this is the only method we shall look at. There are others. We shall see that we have evolutionary strategies. Just write them here. And we also have genetic programming. And then we have genetic programming. So we shall not look at these other two, since they are not so much different from genetic algorithms. They just differ in a few things. So these, we shall not cover them in this topic. So after looking at genetic algorithms, then finally we shall look at a case study where we get to use a genetic algorithm to learn or to determine a schedule, an optimal schedule for a power plant that supplies electricity. The maintenance schedule is supposed to maintain the equipment in the power plant so that they don't fail. But while maintaining, we still want to continue providing power supply. So we need to come up with a schedule that enables that to happen. So we shall see that this is not a simple problem. It is a complicated problem. and sometimes we have to employ evolutionary computation to come up with appropriate solutions. So now let's move on to the introduction. So in this introduction, we try to define intelligence in the context of this topic of evolution. We define intelligence as the ability of a system to adopt its behavior to an ever-changing environment. According to Alan Turing, as you know, Alan Turing is one of the first people who thought about ideas on artificial intelligence. The form or appearance of a system is irrelevant to its intelligence. But we know that from our everyday life, we know that evidences of intelligent behavior can be seen in human beings. That is a given. However, according to Alan Turing, the form or appearance of a system may not be relevant to its intelligence. But we know that we humans are intelligent. So as humans, we believe that we are products of evolution. And so if we can model the process of evolution, we might expect to create intelligent behavior. So evolutionary computation is what tries to simulate evolution on a computer. And the result of such a simulation is a series of optimization algorithms that are usually based on a simple set of rules. Okay, so the simulation itself, in other words, will involve using algorithms that run iteratively. So this optimization will iteratively improve the quality of solutions until an optimal or at least feasible solution is found. So under evolutionary computation, therefore, we try to simulate evolution. And how do we do it? We use some algorithms that iteratively improve the quality of solutions until an optimal or at least feasible solution is found. So in other words, this method works through iterations. One iteration after another, we start with some solutions, arbitrary solutions, and then we go through several iterations as we try to improve those solutions to be able to solve a given problem. But one question you may ask is whether evolution is really intelligent. So in this slide, we are saying that we can consider the behavior of an individual organism as an inductive inference about some yet unknown aspects of its environment. Okay, so we are asking, can evolution be really intelligent? So if we consider the behavior of an individual organism as an inductive inference about some yet unknown aspects of its environment, now, if over successive generations, the organism survives, then we can say that that organism is capable of learning to perceive changes in its environment and therefore survive. So that ability of learning, okay, that ability of learning to perceive changes in the environment and survive is something we can easily associate with intelligence. Okay, so this is the key question here. So how do we define intelligence in the context of evolution? So evolution is about survival, as most of you know. It's about changes and the ability of organisms to survive with those changes. So we are saying that if an organism learns how to survive, then we can associate that with some form of intelligence. Well, we know that evolution itself is a very, very, very slow process from our perspective. Naturally, it is a slow process. So when we talk of simulating evolution in a computer, we shall do things differently. On a computer, the evolution will not take, for example, billions of years. It will take some little time. So to conclude this introductory section, we are saying that this evolutionary approach to intelligence is based on computational models of natural selection and genetics. So we shall be applying a number of concepts associated with evolution, including those of natural selection, genetics, things like aspects that lead to survival, like reproduction, mutation. We shall be using most of those concepts under this evolutionary approach. So in this evolutionary approach, we use computational models of evolution generally, but we can break it down to natural selection and genetics. So under genetics, we have concepts like genes, we have concepts like chromosomes, and a number of other concepts, as we shall see. And we shall use each of these concepts in evolutionary computation. So, so we call these models, the computational models under the evolutionary computation, rather under the evolutionary approach, we call the computational models evolutionary computation. And the term evolutionary computation itself is an umbrella term that combines a number of different methods, 3 to be more specific. The first is genetic algorithms, the second is evolutionary strategies, and the third is genetic programming. So we've said that for us, we shall concentrate more on only genetic algorithms. The others, we shall not have time to cover them. So here we go to the second subsection of this topic, where we talk about the simulation of natural evolution. Okay, but before we talk about the simulation of natural evolution, we are going to give some history about evolution itself. So on 1st July 1858, Charles Darwin presented his theory of evolution before what is referred to as the Linnean Society of London. So this date of 1st July 1858 marks the beginning of a revolution in biology, because in this paper, in this theory of evolution, a new perspective was presented, a new paradigm was presented of how biology should be understood that had never been seen before. So it was not only Darwin who was coming up with new ideas. There were other people, somebody called Weizmann and also Mendel. They came up with a number of ideas. So those new ideas, including Darwin's classical theory of evolution, together with Weizmann's theory of natural selection, and Mendel's concept of genetics, at that time what represented what is called the neo-Darwinian paradigm, the paradigm that is completely associated with evolution. So previously, biology had been understood in some other ways, but now these people had come up with these ideas around evolution with several concepts. So the neo-Darwinian, so this now neo-Darwinian paradigm or neo-Darwinism is based on processes of reproduction, of mutation, and competition and selection, okay, in natural life. So for organisms to survive, they must reproduce. Sometimes there are severe changes, I think, that cause mutations in organisms. And then in the natural world, there is always competition for resources. And also there is natural selection. There's a way things select to their own benefits. Okay, so the power, for example, the power to mutate is guaranteed in any living organism that reproduces itself in a continuously changing environment. Then we have that the processes of competition and selection just naturally occur, normally take place in the natural world, where expanding populations of different species are limited by a finite space or limited by resources. So in that regard, evolution can be seen as a process that leads to the maintenance of a population's ability to survive and reproduce in a specific environment. And that ability is called evolutionary fitness. So somewhere when we are looking at evolutionary computation, we shall also talk about the fitness of solutions. So our populations will be populations of solutions, not of people or other organisms. And the fitness we shall look at is the quality of those solutions. Okay. So in real life, we know that fitness cannot be measured directly. However, it can be estimated on the basis of the ecology and functional morphology of an organism in its environment. So when we look at evolutionary fitness, we can also view it as a measure of an organism's ability to anticipate changes in its environment. So the fitness or the quantitative measure of the ability to predict environmental changes and respond adequately can be considered as the quality that is optimized in natural life. So in natural life, that's how things happen under this context of evolution. So in this case, we are going to illustrate this fitness. We are discussing the concept of evolutionary fitness, the one that makes a population to survive. Okay, so how can a population with increasing fitness be generated? So to illustrate fitness, we can use the concept of, we can use a number of examples. Okay, so here we used an example of a population of rabbits. Okay, we use an example of a population of rabbits. Now, in the population of rabbits, we shall find that some rabbits are faster than others. And we may say that those rabbits possess superior fitness. Okay, and this is the same with people. You might find that some people are more fitter than others. They possess superior fitness compared to others. So in rabbits as well, you find some rabbits that are not so fit, and then you'll find those that are really fit. Now, in the context of rabbits that are very fit will have a greater chance of avoiding predators like foxes. And because they have that greater chance, then they can survive. And when they survive, they can breed and reproduce. Okay. So because of fitness assures some form of survival, some form of existence to perform a number of natural operations, operations like reproduction that ensure that a population, a species continues surviving. It's the case with us human beings. If we decided all of us not to, for example, breed, then our species will completely die out. So if for the species, for the parents that have superior fitness, if you have two parents that have superior fitness, there is a good chance that a combination of their genes will produce an offspring with even higher fitness. Over time, the entire population of rabbits becomes faster to meet their environmental challenges in the face of predators. So as years go on, as generations come and go, the population's fitness continues to increase. The fitness, as we said, is associated with the capability to predict environmental changes and thereby survive. So that ability to predict the environment and intervene is what we associate with generally with the population's fitness. So maybe currently our generations may be more fitter than our parents' generations, but sometimes we think that some of our ancestors must have been fitter than we are now. But probably currently we have a lot at our disposal. We have a lot of information, a lot of knowledge, and therefore our decision-making becomes simpler. And with that also, we are able to do many things as compared to people of long ago. So in this case, we are talking of naturally that in a population, usually fitter individuals will have a higher chance of surviving. And if they get together, they may also produce even more fitter offsprings. Now, under the simulation of natural evolution or evolutionary computation, we shall find that there are several methods that can be used, but all methods of evolutionary computation simulate natural evolution by creating a population of individuals and then evaluating their fitness and then generating a population through genetic operations and repeating that process a number of times. Okay, so this bullet here that you're seeing in this case, this particular bullet summarizes basically what most of the evolutionary computation methods do, that they start off by creating a population. And then once they have created that population, they evaluate the fitness of that population. That evaluation is done for a purpose. It's done to pick out individuals that have a higher chance of surviving. So once we pick out individuals that have a higher chance of surviving, then we use genetic operations to combine those individuals to give us a new population. And once we get the new population, we can check its fitness. We check its fitness as well, okay, to see whether it's good enough. And if it's not good enough, then we repeat the process. We continue creating new populations until we reach a population that is good enough. So these populations, as I've said now in evolutionary computation, will correspond, for example, to solutions to problems, a set of solutions. So if you have a problem, your population could be like 100 possible solutions. And then in those solutions, you'll determine the fitness of each solution. And you find that some solutions are more fitter than others. And then you'll be interested in those solutions that have a higher fitness because you want to bring them and combine them through genetic operations to create a population of better solutions. And you repeat that process through a number of iterations until you come to a population of better fitness. So as I've already indicated and emphasized, that for us, among the many methods of evolutionary computation, we are going to stick to genetic algorithms, as most of the other evolutionary algorithms can be viewed as variations of genetic algorithms. So as we look at these genetic algorithms, we give some background. In the early 1970s, someone called John Holland, one of the founders of evolutionary computation, introduced the concept of genetic algorithms. Holland's aim was to make computers to do what nature does. Okay, that was his aim. Okay, to make computers do what nature does. So in that case, Holland formalized or worked on a number of ideas around how to represent nature or represent concepts associated with evolution in a computer. Now, Holland was a computer scientist, and as a computer scientist, he was concerned with algorithms that manipulate strings of binary digits or strings of bits, because as a computer scientist, and even in the IST world, some of your introductory course units will introduce you to concepts like bits. But of course, these are the low level processing units of a computer. And so at that time, the 1970s, there was a lot of research on what these strings of bits could do. Okay, so Holland was concerned with algorithms that manipulate those strings of binary digits that are referred to as bits. So Holland viewed those algorithms as an abstract form of natural evolution. And Holland's genetic algorithm can be represented by a sequence of procedural steps for moving from one population of artificial chromosomes to a new population. So we've talked about Holland's genetic algorithm that simulates nature by moving from one artificial chromosome to another artificial chromosome. But what is an artificial chromosome? Each artificial chromosome consists of a number of genes, and each gene is represented by 0 or 1. So this is the representation that this gentleman used. And in the figure below here, we show such a chromosome with the genes being represented by those bits by 0 or 1. So each point here is a gene in this kind of representation. And the whole thing is a chromosome. The whole string is what you would call a chromosome. Okay? So now, so now let's move on to discuss more about the, of course, this new representation that tries to simulate evolution. So, of course, when we look at nature, we know that nature has an ability to adapt and learn without being told what to do. In other words, nature finds good chromosomes blindly. In most cases, nature will find good chromosomes blindly. So genetic algorithms try to do the same, okay? So to be able to find good chromosomes and utilize them, there are two mechanisms that link a genetic algorithm to the problem it is solving. And the first is that of encoding. The second is that of evaluation. So before you talk of using a genetic algorithm, you must find an encoding for your problem or for your context. And once you have found an encoding, then whatever you represent using that encoding, you can figure out how to evaluate it, because in nature, in evolution, the concept of fitness is important. Evaluation is mainly aimed at finding fit solutions. So a genetic algorithm uses a measure of fitness of individual chromosomes to carry out some genetic operations like reproduction. So as reproduction takes place, we could use, for example, crossover operators that exchange parts of two single chromosomes, and a mutation operator that changes the gene value in some randomly chosen location of a chromosome. Okay, so genetic algorithms, when we use them, first of all, we have to see what representation to use through encoding, and also determine how to evaluate what we have represented. But of course, when we talk about evolution, we must talk about some genetic operations as well, most especially reproduction that enables a species to survive. So in evolutionary computation or in genetic algorithms also, we try to implement reproduction, okay? And reproduction usually is implemented through what is called crossover. So you have two chromosomes, and then you exchange some of their parts to form two new offsprings, or two new chromosomes. So as reproduction takes place, we usually use that crossover operator to exchange parts of two single chromosomes. Now, we've said that in evolution, mutation can also occur over some time. Okay, so in an artificial context, mutation changes a gene value in some randomly chosen location of the chromosome. So we shall, with examples, look at some of those operations later on. For now, we are looking at some of the introduction to those concepts. But now we are going to look at this genetic algorithm process, or genetic algorithm, in more detail. So in the slide that follows, this particular slide, we have a flow chart that represents a basic genetic algorithm, the steps of a basic genetic algorithm. Okay, so in this flow chart, as you can see, like any other algorithm, we usually have a starting point. So we say that the way evolutionary computation methods work is by generating a population. So this is what follows. This is the next step. We generate a population of chromosomes of a given number. We could say 100 chromosomes. And we represent each chromosome using this lowercase x with the subscripts. Okay. So initially, the first step, after we have decided on how to represent our problem and solutions, is then to generate a population of chromosomes which correspond to solutions, okay, of a given size or given number. Once we generate a population, so this is generating a population. Once we generate a population, then we calculate the fitness of each chromosome. Okay, calculate the fitness of each chromosome. So this, we said that we need to know because we want to choose solutions that are more fitter than others to create new solutions. So the fitness is calculated through what is called a fitness function, and we use fx to denote that function. For example, for the first chromosome, we calculate its fitness using fx1. Now, when we calculate the fitness, it could be possible that at that point we have achieved a set of solutions whose fitness is good enough, and we don't need to generate new populations. So to determine whether fitness is good enough, we have to set some terminating criteria or termination criterion. Okay. So if that termination criterion is satisfied, if our fitness is good enough, for example, then our flowchart takes this branch, okay, to stop. Otherwise, if the termination criterion is not satisfied, that is, we have the no, or our solutions are still not yet good enough, then this is where we are going to go to next. We are going to select a pair of parents from our current population. We select a pair of parent chromosomes for mating or for reproduction. So once we select a pair of parents for reproduction, then we perform reproduction using crossover, okay? So with crossover probability PC, we perform crossover by exchanging parts of two selected chromosomes and create two offspring chromosomes. So we do this until we achieve the population size we are looking at, we are working with. So we do reproduction with crossover. We can also do mutation with the probability PM. So for mutation, we randomly change the gene values in any two given offspring chromosomes. So it is possible that when you make or you mate, when you mate or perform reproduction, okay, using crossover, you end up with chromosomes, child chromosomes or offspring chromosomes that are exactly the same as the parent. So if you have offspring chromosomes that are exactly the same as the parent, then you'll get no improvement in the fitness of the new population. So what you'd need to do is maybe make some changes via mutation, okay, to see if you can now randomly change a gene value such that you make the offsprings a little bit different from their parents with the aim of getting new solutions that have better fitness. So once we've performed those genetic operations of mutation and crossover, then we put our resulting chromosomes in the new population. So we repeat this process until we come to this decision box where we ask whether the number of the new population, the size of the new population is equal to the size we are working with, the number of chromosomes we want to work with, that is N. So if we have not yet achieved the population size, we shall perform iterations where we select a pair of parents to get for us new offsprings, we add them to the population until the size of the population is achieved. So if the size of the population is achieved, then we are going to replace the current chromosome population with a new population, okay? And when we replace the new population, we determine its fitness, we calculate its fitness. That's why we go back through this branch, go back here to calculate the fitness of the new population to see whether the fitness of the solutions in that population is good enough. And if it's good enough, we shall stop. But if it's not, we shall now continue to generate another population. So let's talk about each of those steps in more detail. Here, we shall start. What we show is we are going to describe the major steps of the basic genetic algorithm. So in the first step, step number 1, we have to work on representing the problem variable domain, okay? We must come up with a representation for the problem variable domain in terms of chromosomes. So when we are using evolutionary computation or genetic algorithms in particular, for each problem we work with, we have to determine how a chromosome will be represented. Of course, we have looked at one representation form of, for example, these binary digits, but there could be other representation forms beyond binary digits, okay? So, but the first thing you do is to figure out how are you going to present the solutions for that problem as chromosomes. And there are many things you can consider. Okay. So whenever we specify chromosomes, we usually specify them to a fixed length. For example, in this case, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 12, 13, 14, 15, 16. So this is a chromosome of length 16 because it has 16 genes, okay? Of length 16 genes. So whenever you decide on the representation of a chromosome, you have to also determine how long that chromosome or each chromosome will be, okay? So in addition to deciding how long a chromosome will be, we also have to determine the chromosome population size, and that is denoted as N. For example, I said that you could say, okay, the chromosome population size can be 100, but it can also be 500 or 1,000. You can test whenever you develop your system and use a genetic algorithm, you can test those different options in terms of population and see which population size gives you better solutions. Now, we also have to specify some parameters we shall use for the genetic operations. We have what is called the crossover probability, PC, and we have what is called the mutation probability, PM. So these are used for reproduction in terms of PC, and PM is used for mutation. So in the first step, we must first of all work on representation and then decide on the population size, then the probabilities for reproduction and probability for mutation. In the second step, we define a fitness function. We shall need a fitness function to evaluate for us the individuals, or to evaluate the chromosome population, the chromosomes in the chromosome population. We shall need a fitness function. The fitness function will be used to measure the performance or fitness of an individual chromosome in the problem domain. The fitness function establishes the basis for selecting chromosomes that will be mated during reproduction, because we say that a chromosome or individual that is having more fitness will have a higher chance of surviving and therefore breeding. So this is the same case here. But step number 2, more specifically, we have to come up with a fitness function. Now, the fitness function will vary from problem to problem, just like also in step 1, how you represent a chromosome will also vary from problem to problem. So no standard representation will work for different problems. Each problem, when you are trying to solve it, will demand its own representation for a chromosome and will also demand its own definition of a fitness function. So these first 2 steps are where we get our tools we need to use now for the genetic algorithm, okay? For example, these first 2 steps establish for us the tools we need to use for our genetic algorithm, okay? As you see, there are more of preparatory steps that we have to decide on how to represent our solutions, of what length they will be. We also have to determine how much solutions we can work with in the genetic algorithm. And we have to determine some parameters, specify some parameters like crossover probability and mutation probability. Then the second step, we have to define what fitness function we are going to use for evaluation or for determining the fitness of individual chromosomes. So with each chromosome representation will also come a corresponding fitness function. So now in step 3 is where we start the genetic algorithm in terms of running. So we randomly generate an initial population of chromosomes of size N. This is the first, after the start, we generate a population of chromosomes of size N. So this is what we are doing in step 3. Please note the use of the term randomly, okay? So here we do it randomly so as to simulate nature as much as possible. So in step 3, we randomly generate an initial population of chromosomes of that size. So the chromosomes we said are represented by the X's. So X1, X2 up to Xn. In step 4, now that's where once we have a population of chromosomes, we are going to determine how good that population is. And we say that to determine how good the population is, we have to determine the fitness. Okay, so we have to calculate the fitness of each individual chromosome in the population. And the fitness we calculate using the fitness function. That's why in step number 2 here, we needed to define a fitness function because we are going to use it to calculate the fitness of individual chromosomes in a population. So for all the chromosomes in the population, we calculate their fitness by applying that fitness function. In step 5, when we calculate the fitness of each individual chromosome, we can determine the aggregated fitness of the population to see whether it's good enough to solve our problem. If it's not good enough, we say that we have to now produce a new population. So step 5 is the one that indicates how we can try to produce new chromosomes for a new population. So we select a pair of chromosomes for mating from the current population. So to be able to produce a new population, first of all, you must get parents from the current population. Now, the parent chromosomes are selected with a probability related to their fitness, such that highly fit chromosomes have a higher probability of being selected for mating than less fit chromosomes. In step number 6, we create a pair of offspring chromosomes by applying the genetic operations of crossover and mutation. So after selecting a pair of parent chromosomes in step 5, then in step 6, we can try to perform some genetic operations. For example, for reproduction, mating the two, for example, the selected parents, mating them or breeding them to generate offspring chromosomes. So we say that we can use 2 genetic operations. We can use crossover to exchange parts of the 2 chromosomes, and mutation to change a particular part or gene of 1 chromosome. So once we perform our genetic operations and we come up with the offspring chromosomes, we place the created offspring chromosomes in the new population. So in step 8, we repeat our creation of offspring chromosomes and their addition to the new population until the size of the new chromosome population becomes equal to the size of the previous population N. So we do reproduction and mating, generating new offspring chromosomes until the size of the new offsprings is the same, is size N, the one we decided in step 1, the size we should work with. Now, in step 9, we replace the initial parent chromosome population with the new offspring population. And then we go back in step 10, we go back to step 4 to calculate the fitness of the new offspring chromosome population. Okay, once the fitness is okay, we can stop, but if it's not okay, then we repeat the process until when the fitness is okay or until when the termination criterion is satisfied. So those 10 steps are the ones we associate with a basic genetic algorithm. So this is really simplistic in the way we have presented it here, but when you read some literature, it may look as though it's quite complicated stuff. But these are the basic steps as I've read them. And this figure also summarizes or shows that the process of the basic genetic algorithm. So having looked at the basic steps, the steps of a basic genetic algorithm, we see that a genetic algorithm represents an iterative process where each iteration is called a generation. Okay, so in each iteration, we go through the iterations, creating new populations, creating new offsprings until we create a new population. So after each iteration, we end up with a new generation. Okay, so here we use the term generation as well, just like we use it for people. Like you guys are of some generation, then you have your parents who are of also some generation, then they have their parents also who are of another generation, then there's the other generation. So here we also have a generations of solutions as we iterate. Okay, so each iteration is called a generation. Now, practically, a typical number of generations for a simple genetic algorithm can range from 50 to over 500. So the entire set of generations from the start when we run the algorithm until when it stops after generating like 500 populations or generations, that entire set of generations is called a run. Okay, so one iteration gives us a generation, and then several iterations will give us many generations, and considering all of them together from when the genetic algorithm started running up to when it stopped, that set of generations, we call it a run. Okay, so we've also looked at the genetic algorithm's operation. When it's using its operators, it uses some probabilities, and then it also uses a stochastic method to search for parents that may be good for mating. So because it is using a probabilistic approach, it is probable that the fitness of a population may remain stable for a number of generations. In other words, it's probable that the genetic algorithm will choose parents that when they mate will lead to the same to offsprings that are exactly like them. Okay, so therefore the fitness of the population may remain the same for several generations before a superior chromosome appears. So sometimes a common practice is to terminate a genetic algorithm after a specified number of generations. And then you look at each of the generations and examine what the best chromosomes in the population were. But if there's no satisfactory solution, then we can restart the genetic algorithm to run again. To run, of course, as it runs randomly, maybe things will be different this time round. Okay, so we can have a number of restarts until the genetic algorithm generates solutions that are good enough. So what we've covered is like a theoretical introduction to these genetic algorithms. Now, in this particular example, we are going to demonstrate the application of that genetic algorithm, okay, on a mathematical problem. That's why we are saying that this simple example will help us to understand. It will help us to understand how a genetic algorithm works. Okay, so in this example, the problem is to find the maximum value of this function. Okay, we need to find the maximum value of that function. For those who did some mathematics, this is a quadratic function. And quadratic function usually have curves that have a maximum somewhere. Okay, so you have something like this, and then maybe a curve like that, and the maximum is at that point. So we need to find that maximum. So we could, of course, it would, for quadratic functions, it may be easier to plot the curve and be able to find that maximum. But when the functions become complicated, then plotting them also may not be that easy, especially if they have more than one variable, or they have many variables where you cannot just plot on a two-dimensional space. So, however, this we are using for illustration purposes, just to show you that for this quadratic function, we could try to use the genetic algorithm process to come up with a solution that solves, or that gives us the maximum point where the function, that gives us the maximum point for the function. So here we've been told, let us find the maximum value of that function, where the parameter x varies between 0 and 15. Okay, 0 and 15. So for simplicity, we may assume that x takes only integer values. In other words, since it takes only integer values, in other words, x can be of only those figures from 0 up to 15. For example, in the table down here, we have 1, we have 2, we have 3, we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so those are the 15 values between 0 and 15. Now, as you've seen, when we are working with genetic algorithms, we said that we must figure out a way of representing our variables as chromosomes. So for this particular case, the thought is that we represent these values, okay, as bits, as binary digits. So we change from this hexadecimal, I think, form, is it hexa or base 10 form, to binary digits, okay, to be able to represent or come up with appropriate chromosomes. So when we look at the integers from 1 up to 15, and we consider how many binary digits we need to represent them, at 15, we see that the total number of bits that we need to represent 15 is 4 of them, okay? So that's why we are saying that in that case, if we look at all the other numbers below 15, we shall always find a way of using 4 bits to represent them. That's why we are saying that chromosomes can be built with only 4 genes, and these genes are bits. Okay. So now, with those 4 bits, we can represent one, for example, as 001, 2 as 0010, 3 as 0011, 4 as 0100, and 5 like that. Okay. So we represent one as that, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you have the integer on the left and the binary code on the right. And that binary code is the one that is giving us a chromosome. Okay. So for our problem, we decide that we are going to represent the chromosomes like that. Now, with that representation, the next step of our genetic algorithm, we said we have to, of course, at the first step, we have to come up with the representation, and then we also have to determine. Somebody is asking, is there a formula that uses the binary digits? So this is the elementary mathematics. So like, I think 1, to change to base 2, you would do something. And then for 2, you would also do something. Okay, in other words, 1 divided by 2, for example, is 0, remainder 1. So that is what you would associate. And then 2 divided by 2, you would get 1, remainder 0. And then 3 divided by 2, you'd get 1, remainder 1. And then 4 divided by 2, you'd get, first of all, 2. That is remainder 0. And then since this is divisible by 2, so this you divide by 2, you'll get 1, remainder 0. Okay. So there your friends are talking that you divide, and I think it was something like for 4, you have 4, then 2, you remain with 0, and then 1, you remain with 0. So this side you're dividing, and this side you get the remainders. So what you have here is what you use to represent 4, for example. So this 100 works for 4. If it was 5, you would do 5 divided by 2, you get 2, remainder 1, and then the 2 divided by 2, you get 1, remainder 0. So that you have, so you take this. Okay, I hope, Ronald, you're following. This is elementary math. I forget where I did it, but for the largest number we are using, of course, to fill up the bits, this is what you'll get for 15. Okay, so, and 15 will take 4 bits. So all the numbers we shall find, to represent them, those using these 4 bits. So for 14, we can, this is the binary digits for it. For 13, this is the binary digits. So you need all those. When we come to 7, okay, that's where we add the 0. Okay, so we add the zeros in front. Otherwise, 7 can be completely represented by those 3 digits. Okay, and also when we come to 3, we add 2 zeros. We add those 2 zeros. Otherwise, 3 can be represented by those 2 digits. So that is the binary representation. I think now we have an idea of how it is coming up. So that is the first thing you had to figure out, okay, in our first step. And we also said that you have to determine the population size. Here we have decided that it is 6. And then we also have to determine the crossover probability. Here it is 0.7. The mutation probability is very small since mutation happens rarely. So that's 0.001. And then that would be the first step, if you remember. Okay, if we go back a bit, we said the first step represent the problem as a chromosome. So for us, we have said it will be 4 bits. That is the solutions or the variable. And then we choose the size of the chromosome population, and we've said it will be 6. And then the crossover probability, we have said it will be 0.7. And then the mutation probability, we have said that will be 0.01. Okay, so that is the first step in our example case study. The second step is to define the fitness function. Okay, the fitness function. So our fitness function fx is simply that expression 15x minus x squared. And we shall see how we use it. Okay. So once we have performed the first 2 steps, in the third step, we say that we generate a population of those chromosomes. Okay, we generate chromosomes randomly up to the given population we are working with. So here we have our population size is 6. So the first chromosome, we label it as X1, the second as X2, the third as X3, the fourth as X4, the fifth as X5, and the sixth as X6. Okay, and then we specify. These are just labels, but the actual generation actually is these binary digits or representing chromosomes. So actually, we randomly generate these strings, binary digits, 4 in size, for 6 chromosomes. Okay, so such that I think now I should remove this and say that actually we start this way by generating these chromosomes here, and then we label them. So that will be the label for that second chromosome, that will be the label for the third, that will be the label for the fourth, this will be the label for the fifth, and that will be the label for the sixth. So this is the step 3. Okay, step 3 happens here. We generate a population of chromosomes of our size 6 of them. Okay, and this is what we generate. Now, step number 4 is where we calculate the fitness. So step 4 is here. We calculate the fitness. Now remember, our fitness function is fx is equal to, if we go back here, it is 15x minus x squared. Okay, 15x minus x squared. So that is our fitness function. But given these chromosomes, how can we determine the fitness function? So to determine the fitness, rather their fitnesses, we first have to now convert them back to base 10. Okay, convert each of them back to base 10, such that you have the x value here. So for example, this particular chromosome here, 1100, is 12. This 0100 is 4. 0001 is 1. And 1110 is 14. And 10111 is 7. 1001 is 9. So once we have that x, then we can feed that x into this expression, 15x minus x squared. For example, where x is 12, okay, that will be 15 times 12 minus 12 squared. Okay, so 15, for example, times 12 is equal to what? What is 15 times 12? Should be something like 195. Okay, so if you subtract that, So sorry, I had to receive the call and I'm using my phone for the data. So I hope I am back, and I hope we are back at the screen where I stopped. All right. Then I think we can continue. So I was saying that for each of these chromosomes that we have created in step number 3, we are going to calculate their fitness, and calculating their fitness involves first transforming back to base 10 and then putting that value in the fitness function. So for 12, I was saying that 15 times 12 is something like 144 plus 36 is something like 180, I think, 180 minus 144, which gives us the 36. And then likewise, for 4, you'd get 15. Yeah, for 4, you get 15 times 4 minus 4 squared, which is 60 minus 16. And that gives you the 44. So for the other functions as well, this is for 1, it will be the easiest. That would be 15 minus 1, you get the 14. For 14, it seems you'll also get 14. And then for 7, you'll get 56, and for 9, you get 54. So when we calculate that fitness, we can determine the fitness ratio to show us which chromosomes are relatively fitter, have a relatively higher fitness. So this we provide in this last column here. For example, the first chromosome has a relative, or rather a fitness ratio of 16.5, and then the second has 20.2, then the third 6.4, the fourth 6.4, the fifth 25.7, the sixth 24.8. So this is a percentage, which means that they add up to, we calculate, we multiply, we calculate the total. That is, we calculate this 36, first of all, plus 44, plus 14, plus 14, plus 56, plus 54. To get a total, we add them up to get the total. Then for each of them, if our total is T, we divide by T times 100%. This is what gives us the fitness ratio. I hope that answers Michael's question. So likewise, here we get divide by that total times 100 gives us the fitness ratio. Okay, so that is step number what? Step number 4. Okay, step number 4 is where we determine the fitness and also that fitness ratio, because that fitness ratio or value will help us to determine parent chromosomes. So for now, you can maybe not be so much concerned about the graphs down here. What they are showing is that initially, the initial chromosomes we generated, that is X1, for example, X1, for example, takes a value of 12. So 12 is here. That's where X is, and that's where it will fall on that function. So this is X1, and then X2 is 4. So this is X2, and this is the point at which it will be on that function. And then X3 is 1. This is X3. That is the point at which it will be on that function. Okay, that is, it will, the fx will be 14. And then X4 of 14, this is X4. This is the point at which it will be. This is also 14. And then X5 of 7, 7 is here. X5, that is X5, that is the point at which it will be. And then X6 is 9. This is X6. This will be the point at which it will be. So clearly you see that X5 and S6 at a higher points on that function, representing their relatively high level of fitness. So we would like to see that most of the fitnesses of each of these chromosomes moves up to the maximum, okay? So when we continue iterating, what we see on the right here will be that process where we have most of the fitnesses have moved up to the maximum point up there, okay? So in so somebody has asked, what's the advisable number of chromosome strings to use? Is it 6 or it can be any number? So the chromosome number size or population can be any number. You can vary it. It is something you can vary. Yes, so during mating, now we are going to step number 5. If you remember the process, in step number 5, we select a pair of chromosomes. So this is, in our example, this is what we are going to discuss now. Okay. So in step number 5, we select, if I go back again very fast, we select a pair of chromosomes for mating. So here we are saying that in natural selection, only the fittest species can survive. And because they can survive, they can breed and thereby pass their genes on to the next generation. So in evolutionary computation, the genetic algorithms we are using also will use a similar approach. But unlike nature, the size of the chromosome population will remain unchanged from one generation to the next. Okay. So because at the start here we said we are going to work with a size that is 6 chromosomes, that is the same size we have started with, okay, here in this figure. So this is the number of chromosomes we started with, okay? They are 6 in number. N is equals to 6. So in this case, we are saying that when we are using genetic algorithms, our size of the chromosomes population will remain unchanged. In other words, we shall select parents and then we perform genetic operations to create offspring chromosomes. But the new population will not exceed 6 chromosomes. It will also be 6 chromosomes. So for the selection of the parents, we said that the fitness may be important. That's why in the previous slide, we saw that the last column in the table shows the ratio of individual chromosomes fitness to the population's total fitness. And that ratio determines the chromosome's chance of being selected for mating. Okay. So now we shall see that as we generate new chromosomes and new chromosome populations or generations, the chromosome's average fitness will improve from one generation to the next. This is what we should expect, that as we continue producing new chromosomes, the new chromosomes we have produced should have a higher fitness than their parents. So the population of the new chromosomes should have a higher fitness than the population of their parents. So there are several methods we can use for selecting parent chromosomes. And here we just look at one of the most commonly used one. It's called the roulette wheel selection method. Okay, the roulette wheel selection method. In the figure below, we just illustrate that roulette wheel. Roulette wheel is a wheel that has a number of sections, more like a pie chart, and a pointer that when you roll it, it rotates and it comes to rest somewhere. And you see where the pointer sits, that's where your interest will be. So in the roulette wheel selection method, what we are going to do is to place the fitness ratios we calculated for each of the chromosomes. For example, that for this particular section, that is occupied by the fitness for the first chromosome, and this one in blue is occupied by the fitness for the second chromosome. the third in purple is occupied by the fitness for the third chromosome. This other one in something like orange is occupied by the fourth chromosome. And then the one in, I think, light something like green is occupied by the fifth chromosome. And then the dark one is occupied by the sixth chromosome. So you see that the chromosomes with a higher fitness ratio will stand a higher chance of the roulette wheel maybe having the pointer rest in their sections. Okay. So so this was the fitness ratio for the first chromosome. And then when you add 20 to this, 20.2, you get that this is 36.7. Remember, the fitness ratio is in percentages, so it's not in degrees. So we are looking at percentages for the whole wheel. So when you add 6.4, you get 43.1. When you add 6.4 here, you get 49.5. And when you add 25.3, you get 75.2. And then up to 24.8, you get 100%. So, but the idea is that each of the chromosomes has a section on the roulette wheel. And when you roll it, the pointer will come to rest somewhere. So there are higher chances that chromosomes that have bigger portions of the wheel will stand a chance of the pointers staying put in their sections. So when you roll the roulette wheel, you roll it a number of times, and then first you roll it one time, you select one of the parents, then roll it another time, you select another parent. Okay. So so somebody has asked, what happens if it lands on the smallest? That's also okay. You select that one because the process is stochastic. There is a probability that the smallest one can also have a chance. And this is in real life. It's an example I usually give in class, that sometimes you find people who you do not expect to match together, but there's a way they hook up and eventually lead on their lives. But you really say that they are a mismatch. So in this case as well, the smallest chromosome, the chromosome with the smallest fitness, also has a chance. There's a chance that it can be selected, but the chance is small. Most likely it will be the ones that have a bigger fitness that will be selected. But it also has a chance. And if it is the wheel, it lands on the smallest, we select it. So that is by the rules of the game. Okay, so so that's why it's called a roulette wheel selection method. Whenever you go to those lottery things and you rotate it, and where the pointer stays, that's the money you take. No one says that the money is small. That's where it landed. That's the money you take. If it landed that there was no money, that's what you go with. Those are the rules of the roulette wheel, and those rules we use here also in selecting the chromosome parents. So after selecting the chromosome parents, we can now start doing the reproduction, for example. And we said that we do reproduction using the crossover operator. We do reproduction using the crossover operator. So in this case, in the crossover operator, we have an initial population of 6 chromosomes. Of course, that is what we have initially. And what we want to work towards too is a new population again of 6 chromosomes. Okay. So therefore, to establish the same population in the next generation, then we would have to rotate that roulette wheel 6 times. Okay. We have to rotate the roulette wheel 6 times. So when we do that, we shall select a number of parents. Okay. We shall select 6 parents. So when we rotate it 6 times, it will give us 6 parents. and it is those that we are going to use to try to generate a new offsprings. So from the 6 parents, we can choose a pair of parent chromosomes where we apply the crossover operator. Okay, so in this case, we give more details about this crossover operator. What it does is that it randomly chooses a crossover point where 2 parent chromosomes break, and then exchanges the chromosome parts after that point. I will illustrate how that is done. So when we exchange the parts of the chromosomes, then we get new offsprings. Okay. Now, it is possible that a pair of chromosomes does not cross over, in which case the chromosome cloning takes place. So here we encounter the term cloning, where we generate exactly the same, where the offspring chromosomes are exactly the same as their parents. Okay. So we try to cross over the parents, but in the end, we end with the exact copies like the parents. Okay. So in this case, the offsprings are created as exact copies of each parent. So now let's illustrate this crossover operator in a diagrammatic form. So here we have our parents, which have been selected from the roulette wheel. In this case, we are saying that X6 here is a parent, X2 here is also a parent. Now, X6 came as like that. X6 is, this is as 1, 0, 0, 1. That is what X6 we chose from our roulette wheel. And then X2 is 0, 1, 0, 0. So the crossover operator, the way it works is we say that it randomly chooses a crossover point where 2 parent chromosomes break. Okay. So here, the crossover point is the midpoint of each chromosome, like at that point. Okay. So here we can break the parent chromosomes at that midpoint. Okay. Likewise, this one, we can break it at that midpoint. So then we say that then we exchange the chromosome parts after that point. Okay, so what we are going to do is we are going to get this part, which is after the break point, and also this part, which is after the break point, and we exchange. Okay, so we bring this one this way, and we take this one this way. That is what is illustrated in this figure here, that we break at this point here, we get this part, we take it this way, and then we break also this one at this point, we get this part, and we take it this way. Okay. So so here we do crossover with between the first 2 parents that were selected and the next 2 parents that were selected. So in this other case, in this other particular case, you see that the breakpoint is after the first chromosome. Okay, after the first gene rather. So likewise, we break from there, and what comes after, in this case, we take it this way, and also what comes after here, we take it this other side. Okay, we exchange the parts. Okay, in that way, we shall end up with new chromosomes. So when we exchange, for example, when we bring 0, 0 up here to this side, the new chromosome, what we shall call X6I prime, will be 1, 0 plus the 0, 0 we have brought. So here we shall have 0 and 0. Okay. So this is the offspring chromosome. Okay. The offspring chromosome that results. And then this side also, we shall have that when we bring the 0, 1, we shall have 0, 1, 0, 1. This is X2 prime. Okay. So those are the new offspring chromosomes. Likewise, in this case, we shall have 2 new offspring chromosomes. We shall have that when we bring the 1, 1, 1, now everything will be 1, 1, 1. And then this side, when we bring the 1, 0, 0, so we shall have 0, 1, 0, 0. Okay, so these are the new offspring chromosomes here. Okay, and then this is X5 I prime. Okay, now the last, these ones maybe our crossover probability did not choose them, so we may not perform crossover on them. Okay, we may maybe do something else like mutation on them. So I hope you understand the crossover process. I've illustrated it in all these examples where it is taking place. So now we go to look at the mutation operator. For the mutation operator, we have a change in the gene. Now the mutation operator is considered a background operator. Its role is to provide a guarantee that the search algorithm is not trapped on a local optimum. Okay, so when we are searching, for example, we could have other types of functions. We could have a function that goes here like this, okay, that has a number of peaks. Now, our search algorithm may end up at this peak here, and it thinks that it has found the maximum, okay, and then it stops there, yet there is a higher peak at that point. Okay, so we are saying that the lower peak is what we call the local maximum. That is what we call the local maximum. The higher peak is what you'll find being called the global maximum. Okay, so our aim is to reach this global maximum and not stop at the local maximum. So here we are saying the role of the mutation operator is to provide a guarantee that the search algorithm is not trapped on a local optimum, okay, like this one here. We want it to continue and end up on the global optimum. So, so what does the mutation operator do? For it, it flips a randomly selected gene in a chromosome. It flips a randomly selected gene in a chromosome. So the mutation probability, of course, the probability we are using for mutation is very small in nature, and it is also kept very low in evolutionary computation. For our genetic algorithms, we also keep that probability as small as possible because in nature, mutation happens rarely, okay? So in genetic algorithms, the typical range is that we can give a mutation probability of 0.001 or up to 0.01. So there are questions that have come up in the chat that under what circumstances would we use a breakpoint of 1 or 2? So that depends on the probabilities you're using. Okay, the probabilities will, for example, indicate that maybe you decide, or randomly you can choose any crossover point. So that is not cast in stone. You could break off, exchange the one end of the chromosome or the starting part of the chromosome or the midpoint of the chromosome. That's where you break from. It's not cast in stone. And then some more light on the local and global maximum. So the local, I was saying that you may have a function that has a number of peaks. So the highest peak is what you call the global optimum. And these other lower ones are what you call local. All the lower ones are called local. So when you're looking for the maximum point, you want to get to the global optimum and not the locals. You want to, so sometimes a method may come and think that it has reached a maximum there. and it stops there. It just gets stuck there because for it was told you go and look until where you are not supposed to go down. Okay, that's where you stop from. So it stops there, and yet there is another peak there. Okay, so the aim is to try to jump away from these local points and reach the global point. Okay, for example, you're going to climb one of the mountains in Uganda. You reach some peak and you think you've reached the top of the mountain, because in other words, you have to again go down, and yet you know there's the highest point somewhere else. The aim is always to reach that highest point. So the highest point is what you call the global point, and all the lower points are called local points. So in this case, we want to always reach the global point. So mutation, so as you can see, these are the ones we generated from crossover. The first two we generated from crossover. Even this one we generated from crossover, the one we had everything one. Likewise, this we generated from crossover. And this, because of the crossover probability, we did not touch them. Now, when we are applying mutation, again, we can choose one of the chromosomes, even the new offspring chromosomes from crossover, and choose a point where we flip them. Okay, so here, for example, we choose the second gene. That is the one that is flipped from 1 to 0. Okay, so that's why we end up with 0 here. So our chromosome here, this side would be 1, 0, 1, 1. And then we jump this and then go to the next, and we choose maybe the third point or third gene, and we flip it for it. Once we flip, we get 0, 1. The 0 changes to 1, and we get 0. So here, this the one with two quotation marks there. Those are the ones that are as a result of mutation. Okay, those are as a result of mutation. So here you get to see that we mutate one of the parent chromosomes that we did not use in crossover. And then this one is the one that remains the parent chromosome that we haven't touched. Okay. So the whole crossover and mutation process is, and also the selection process is summarized in this diagram. That once we have our initial chromosome population, we can apply the roulette wheel selection method to select parents. And for example, these are selected after spinning 6 times. And after spinning 6 times, then we can select those parents. After selecting those parents, we can apply crossover. So crossover is where now we end up with new offsprings. We shall have new offsprings here. In this case, wherever we are performing crossover, we shall have new offsprings. Okay. And then these are some of the parents that we selected that we did not apply crossover. So we move on to mutation, where we now, after doing crossover, we have some new offsprings there, including this as well. But on these new offsprings, we also apply mutation. Okay, we mutate. These are new offsprings. We also mutate on some of the parents' chromosomes that we do not apply crossover. And maybe this time we have our new, in the end, after this, we get a new population. Okay, so you can note that sometimes you don't have to do anything to some of the parents. You can assume they just continue. There's the way they just continue as offsprings to the next generation. So our previous generation, we call it generation I. This is the fitness values it had. The new generation that we have generated, the new population that we have generated, is referred to as generation I+1. And you can see that the fitness values are a bit higher, relatively higher than in the first case, in the first generation. So if you compare, so this particular population, this generation is generation, if I say the fitness of generation I+1 is much greater than the fitness of generation I, okay? So because you see, in this case, you calculate the average fitness here, and you compare to this one, you see this one is bigger, okay? It's much bigger. So as we go through the generations, we expect that the fitness of our chromosomes or offspring or new generations increases until we reach an optimum level. So this is another case study where we get to also show how things now can become a little bit different, okay, in terms of the genetic algorithm process. As I emphasized, I said that each problem will demand its own representation of chromosomes and therefore its own fitness functions, and maybe sometimes also its operations in terms of genetic operations. Okay, so here we have another mathematical function whose maximum or peak point we need to find. We need to find using genetic algorithms. Okay, so suppose it is desired to find the maximum of the peak function of two variables. So this time our function has two variables, x and y, and the function, the expression is on the right here. We have 1 minus x squared e to the power negative x squared minus y plus 1 squared minus x cubed minus y cubed e to the power negative x squared minus y squared. So naturally, or in ordinary situation, it may be difficult for you to determine or to compute the maximum of this function just like that. I don't know what kind of calculus you have to use, but it will be a little bit more complicated. So in this case, you may call on this approach of genetic algorithms and try to see if you can work out, you can try to use these concepts of initial chromosomes and then as solutions, and then you know, the generation of new chromosomes to see if the solutions improve to give you that maximum point. Okay, so in this case, we are told that our variables or parameters x and y vary between -3 and +3. Okay, so the problem is that we need to find, okay, to find the maximum of the peak function, we need to find a value for x and a value for y that makes, or that is at the peak of this function. So as usual, the first step of the genetic algorithm is to figure out how to represent the problem variables as a chromosome. We must always figure out how to present the problem variables as a chromosome. So in this case, there are more details to how this was figured out, but we just try to demonstrate that now here the representation will be a little bit different, okay? So in this case, at the end of it all, after looking at how the solution could be represented, it was figured out that maybe the parameters x and y can be represented as a concatenated binary string, okay, as shown in this particular figure. So you have the first part of the chromosome being taken up by x and the second part of the chromosome being taken up by y. So this is the representation, okay, that was figured out, and you could use other representations as well, but for these people, this is what, you know, came out easy in this case. That let's use 8 binary digits to represent x and also 8 binary digits to represent y. So when we do this, when we transform the digits to base 10, we shall not only stop there, but we shall also transform them to this scale of -3 up to +3, okay? But at least at first, you must come up with a way of representing a chromosome, of representing the variables as a chromosome, because in the end, you need to, you will be working with those variables to determine the fitness or the fitness value using that expression. But first of all, you must have a representation in form of this chromosome in the form of a chromosome. So here, this the chromosome was 16 bits, with the first 8 bits being occupied by the first variable and the next 8 bits occupied by the next variable. So in the first steps of the chromosome, genetic algorithm rather, we also saw that we choose the size of the chromosome population. For example, in this case as well, we could say that the population should be 6, okay? We can maintain 6, or we can say 10. That's also okay. This number is not cast in stone. It can vary. And then once we decide on that, we said we also need the crossover probability, the mutation probability. And then in step number 2, we needed to define the fitness function, okay, f, x, and y. That's what we see on the previous slide. So in step number 3, that's where we now randomly generate the initial population. We randomly generate the initial population. In other words, we shall generate chromosomes of this length, okay, 16 bits in total, 6 of them in a random way, okay, with random bits, and that is the starting point. So once we generate the population, we saw that in step 4, so this is step 4, we calculate the fitness of each chromosome, okay? So now in our example here, that fitness will be calculated in 2 stages. So first of all, a chromosome that is a string of 16 bits will be partitioned into 2 8-bit strings. So we shall, for each of the chromosomes, there will be 16 bits, but we shall subdivide them because we need to find the corresponding X's and Y's, okay? So these strings are converted from binary base 2 to decimal base 10, okay? So for example, this particular binary string for X, once we convert it from base 2 to base 10, now base 10 here, you see that we multiply. We count backwards, okay? 1, 2, 3, 4, 5, 6, 7, okay? So the first here, the first number there, we shall do 1 times 2 to the power 7. And then the next, these zeros will go likewise. So here we multiply to convert from base 2 to base 10. We shall be multiplying with the appropriate powers based on the positions, okay? So when we convert this binary string to decimal, we get 138 base 10. In other words, we get 138 here. So this is X in base 10, okay? And then if you convert the second string, this part for Y, we see that that one would be 59 base 10, okay? So that is Y base 10 is 59. So now we said that we do not stop at this point at converting the bits to base 10, but we must also convert them to this range, -3 to +3, okay? And this is what we do on this slide, that now the range of integers can be handled, that can be handled by 8 bits, okay? That range of integers that can be handled by 8 bits is 2 to the power 8 minus 1, and that is 256 minus 1. 2 to the power 8 is 256, okay? So if we are using 8 bits, okay, the integers that can be represented by 8 bits is 0 to 2 to the power 8 minus 1, okay? So that is 0 to 255, because 2 to the power 8 is 256 minus 1. just like we had the number of integers that can be handled by 4 bits, we had that goes to from 0 to 15, because at 15 is where that is like 2 to the power 4 minus 1. Okay, 2 to the power 4 is 2 times 2 times 2 times 2, which is 16. And then minus 1, that gives you the 15. So that was for 4 bits. That was our previous example. But in this case, we are saying we are working with 8 bits. Okay, so we have to establish, first of all, the range that is represented by 8 bits, because those are the ones that we are using for each of these partial, for each of x and y. They are the ones we are using for those variables. Okay, so we are saying that that range is from 0 up to 255. So now we need to convert this range to the range -3 to +3. Okay, so whatever figure we get in this range, we map it to this range. So we are saying that that range of integers, which can be handled by 8 bits, that is the range from 0 to 255, is mapped to the actual range of parameters x and y. And the actual range of parameters of x and y is -3 to +3. So -3 to +3, if you plotted on a, so you have -2, -1, 0, 1, 2, 3. Okay, you go 1 step here, 2 steps here, 3 steps here, 4 steps here, 5 steps here, and 6 steps here. So that's why we have that 6. Okay, so we are going to divide that 6 against the range of the base 10. The range, yes, of the base 10, 256 minus 1. And that gives us, that is the unit conversion we shall get. Okay, so here we are saying now to obtain the actual values of x and y, then we are going to multiply their decimal values by this unit of transformation. So we are saying that we multiply, first of all, 138 times that unit of transformation, and then we add it to the starting point of this second range here. Okay, we add it to -3 to get where it will lie on this range. Okay, so we see that it will lie at 0.247. Likewise, for 59, we multiply by that unit of transformation. We add it to the starting point of that -3 to +3. So that's why here we have the minus symbol. That's how it is coming about. So we add it to the starting point. Okay, so if the range was starting at 0, then we add this to 0. Okay, if it was starting at 2, then we add this to 2. So that's how the conversion is happening in this case. So here we now transform the base 10 values to that range of -3 to +3. So for 138 base 10, we get 0.247. For 59 base 10, we get -1.6117,647. Okay. So now once we have these ones, we can fit them in this expression here to calculate the fitness. Okay, fit them there to calculate the fitness. So using the decoded values of x, y, and as inputs into the mathematical function, the genetic algorithm calculates the fitness of each chromosome. So now, of course, that is just calculating the fitness. Now in step 5, step 6, step 7. So step 5 is where we said we select the parent chromosomes. Okay, so and then step 6 we use crossover. So in step 6 here we use crossover with the probability equals to 0.7. Step 7 we use mutation. Okay, so we use mutation with probability of this. So we use those on the chromosomes to, first of all, we select parents. Then we use crossover to generate new chromosomes. You use crossover and mutation to generate new chromosomes. Okay. So in step 8, this is where we would repeat the process 5 to 7 until we have size n. Okay. So as we said, a common practice is to specify the number of generations also. Okay. So so we could specify, because this is a more complicated function, we could say that we could have up to a given number of generations, maybe 100, maybe 1,000. That could be the termination criterion. Termination criterion. This could be for step 10, that we do our process for example, 100 generations. So in this case, the genetic algorithm will create 100 generations of 6 chromosomes before stopping generally. So that will be the termination criterion of step 10. Okay. So step 9 is where we iterate, I think, as well. We check to see whether we have, we iterate with the fitness. We go back and check the fitness. Step 10 is when we terminate, I think. So these are, all these steps are combined in here. And in this case, the key involving parts were this one, where we represent the chromosomes by 16 bits, 8 bits occupied by one variable and 8 bits by the other. Then the conversion from the bits to the base 10, and then from base 10 to the range as specified in the problem. And then the use of the converted values to determine the fitness. And then from the fitness, we can follow the calculation for the parents, with selecting the parents and applying the genetic operations. So in this case, we get to see a visualization of the chromosome locations on the surface of the peak function at the start in the initial population. So if this is our surface, that squared portion is our surface, you can see that it has a number of peaks. There's that one, there is also that one. But at the start, since we start out randomly, our positions of the chromosomes is all over the surface, okay? They are all over the surface. So as we now continue iterating, then you see that the location of the chromosomes now start approaching some of the, they start approaching some of the peaks, okay? So here we get to see the chromosome locations on the surface of the peak function after the first generation. And as we continue, okay, after 100 generations, for example, after 100 generations, then all the chromosomes will have moved and peaked at one of the peaks. But here, when we look at the peak they have gone to, that is a local maximum. It is a lower peak. It is not the highest peak. So we could do some changes. And to be able to, for example, we could do mutation so that the chromosomes can work their way around and maybe go to the global maximum or the highest peak. Okay. So here we get to see the performance graphs for 100 generations of 6 chromosomes. And here is where now we see that, okay, here we have used a crossover probability of 0.7, a mutation probability of 0.1, and then we've run 100 generations of a population size of 6 chromosomes. Okay, so this is the result we get in this case. Okay, that this is the behavior of the fitness values. So we see that, okay, the fitness increases and then it stays constant. Then at 50 generations, it shoots up a bit and then also stays constant there. So we can vary one of these. We could vary crossover probability, mutation probability. We could also vary the generations and the size of the population. Okay. So somebody asked, in biology, we consider mutation to be lethal. How is it in computing? So in computing, these things are artificial, so they have no effect on anyone. In fact, mutation in computing tries to help us to get to the global maximum. If you remember, that is what we want to get to, the most highest point or the best fittest point. So it is much better in computing. In biology, of course, it can be either useful or very bad. Okay. So so we are saying that we can vary any of those parameters. We could vary how many times, how generations we train. So as we go on, here now you see that we change the mutation probability to 0.01. We still have 100 generations of 6, each of a population size of 6. And here now you see that in this case, the fitness increases a bit higher, okay, as compared to what we had before here. We see that with these changes in mutation, the mutation causes big jumps, okay, but the fitness increases. And as we continue making changes, so here we have performance graphs for 20 generations, but with a bigger population of 60 chromosomes in each generation. So we see there is a the average increase there. It increases smoothly because we are using so many chromosomes, and this is the best. This is the best population, I think, or generation that, or the best result from the different generations. Okay, so these figures show that you could vary. So here we changed back the mutation, but now we varied the size of the population and also the number of generations, and we ended up with different fitnesses of performance in fitness. If we compare here, we change the mutation to a much higher value, and this was the result. So these performance graphs tell you an idea of how your genetic algorithm is doing in trying to find solutions. Okay, so now we shall wind it up by looking at a more realistic case study, and that is of a case study of maintenance scheduling. So we are going to look at this case study of maintenance scheduling because one of the most successful areas for applying genetic algorithms is in the problem of scheduling resources. Now, most of the scheduling problems are really complex and they are difficult to solve. So sometimes they are approached with a number of different types of methods, but genetic algorithms have found a lot of success in most of the scheduling problems. So there are a number of reasons that are given as to why the scheduling problems are very complicated. You know, they have said that they are unmanageable. They cannot be solved by some techniques. And also using, for example, heuristics cannot guarantee the best solution. But also the main issue is that scheduling problems involve a competition for limited resources. As a result, they are complicated by many constraints. Okay, they are complicated by very many, very many constraints. So in our case study, before we look at it, we can first of all talk about a typical process, the typical process of genetic algorithm development, developing a system that uses genetic algorithms. So these are the steps involved in a typical process of using a genetic algorithm. So the first step is to specify the problem. So this is in the more project context, project-wise context. Assume that you are working on a project and you're saying that you're going to develop a system for scheduling some resources, okay? And now in your practical work or report, this is what you'll be reporting, what you did. First of all, you specify what the problem is more clearly, okay? So when you specify that problem, then you define the constraints that are associated with that problem and what you want to optimize, the optimization criteria. Maybe you want to have like that you have enough reserves of the resources available in case they are needed. So when your program is finding a schedule, then it optimizes on how much resources are reserved or are available. So after that, then you can now start thinking of how to represent your problem domain as a chromosome. So I said that coming up with chromosome representations differs from problem to problem. There's no one defined representation that works for different types of problems. Each problem will demand you to represent, to have a different representation for its chromosome. So like where we had for the function fx is equal to 15x minus x squared, we saw that we have to use 4 bits, okay, in that case. Whereas for that function fxy, we had to use 16 bits, okay, a chromosome of 16 bits. So here, likewise, we are going to see that the chromosome takes on a completely different form. Okay, we shall see that the chromosome takes on a completely different form. So you have to represent the problem domain as a chromosome. Then number 3, you have to define a fitness function to evaluate the chromosome performance. Okay, so we must determine what the fitness function is. And then number 4, we can construct the genetic operators. And then lastly, we run the genetic algorithm and tune its parameters. So in this case study we are going to go through those 5 steps. So I will define this problem that we are going to look at. The problem we are going to consider in this case is a maintenance scheduling in a modern power system. Okay, it is trying to establish a maintenance schedule. So by maintenance scheduling, it means that you're going to maintain some machines in the power, modern power system, maybe machines that generate power. Imagine maybe they are like generators. So you're going to maintain generators, but since these generators serve clients, you want to establish a schedule of maintaining some of the generators while the others are still working, okay? So that the clients don't lose out on power, because there are some critical clients like hospitals where power is needed all the time. So what you want to do is to ensure that they have power all the time. So you need a maintenance scheduling that while you're maintaining the generators, you continue serving power to the clients. So such a maintenance task has to be carried out under several constraints and uncertainties. For example, there could be failures with the generators, there could be forced outages of the power equipment, and there could be delays in obtaining spare parts if some of the generators fail, okay? So that is the complexity associated with the task. So also the maintenance schedule may have to be revised at short notice. So usually you have human experts who work out the schedules by hand, and in that case also there's no guarantee that the optimum or even near optimum schedule is produced if you have experts working out the schedule by hand, okay? Sorry. So now we are going to look at the specifics of the we are going to look at the specifics of this problem, of the case, and as we look at them, we shall go step by step. Okay, so of course the first step we said is to specify the problem. The first step is to specify the problem. So here we have jumped a number of details. We have come direct to the constraints, but specifying the problem, step one, specifying the problem is the most important step in trying to use or develop a genetic algorithm. Because if you do not specify the problem correctly, then you may not obtain a viable schedule, for example, in this case. So in our particular case here, we have that power system components are made to operate continuously throughout their life by means of preventive maintenance. Okay, so when you do preventive maintenance, then you can assure the continuous operation of those power system components or the generators. So the purpose of maintenance scheduling is to find the sequence of outages of power units over a given period of time. It could be like a year, such that the security of a power system is maximized. Okay, so so in other words, during maintenance, you want to avoid those power outages and maximize the security of the system. So any outage in a power system will be associated with some loss in that security. Okay, so so therefore, when you're looking at the how to define the fitness or the performance of the schedule in this case, then you have to determine what its security margin is. We have to determine what are the net reserves that can be provided during maintenance. Okay, so so those are some of the details associated with this particular case problem of ours. Most of the details are provided in the book. Here I'm really rushing over them, but the problem that we want to work on is to schedule a maintenance process while ensuring that power is provided to clients. And the optimal thing we want to have is that we have enough power reserves, just in case anything happens, we have enough power reserves to continue supplying the clients. So so in this slide, we are provided with the constraints, the problem constraints, and here we are told that that the maintenance will take place through 4 intervals. The maintenance will take place through 4 intervals, and during those 4 intervals, these are the maximum power loads that are expected. In other words, during the first interval, 80 megawatts should be expected or be served to the clients. In the second interval, we have 90 megawatts. In the third interval, we have 65 megawatts. And in the fourth interval, we have 70 megawatts. Okay. So, so the key constraint here is that one constraint is that maintenance of any unit starts at the beginning of an interval and finishes at the end of the same or adjacent interval. So in other words, when you're maintaining one of the power units, okay, once you begin maintenance, you could either, when the maintenance starts in one of the intervals and either stops in that interval or can overlap and go into the next interval, but there's no unit that can be maintained over 3 intervals, for example. Each unit, the maximum maintenance intervals that it can take is 2. So this is one of the constraints. So this is a constraint that each of the power units that we are going to maintain can only be maintained either within an interval or across two intervals. So the maintenance cannot be aborted or finished earlier than scheduled. And then also we have that during maintenance, the net reserve of the power system must be greater or equal to 0 at any interval. Okay, the net reserve must be greater or equal to 0 at any interval. So in our case here, the optimum criterion or optimum criterion we are interested in is the maximum of the net reserve. Okay, so if we have more reserves, that is good for us, or that's good for the company. So you need more reserves at any maintenance period. Okay, so this is associated with the first step, specifying what the problem is and identifying what its constraints are. So once you're clear on that, then you can we shall move on to the next phase. But again, this other slide also gives us details about the problem. In this case, in this slide, we are given that we have 7 units. Okay, we have 7 units that are going to be maintained. I feel like I need to instead maybe share the book, because this is not correct. It's supposed to be unit number 1, unit number 2, unit number 3, unit number 4, unit number 6, 5, 6, 7. So so for the unit details, the ones that are going to be maintained, okay, maybe the generators. Here we are told that unit generator 1, for example, its capacity is 20 megawatts. Generator 2, its capacity is 15 megawatts, and generator 3, its capacity is 35 megawatts. This generator 4 is 40 megawatts, 5 is 15 megawatts, 6 is 15 megawatts, and 7 is 10 megawatts. So in doing the table here, some of the figures instead ended up this side. So that's why I feel like I need to go to the book, maybe not to confuse you a lot. So I will maybe just escape a bit from here. And then upload the book. That's where I think the better. I'm trying to download the book so that I think the description of the case study is better there than what I have here. So you just a few minutes and then I'll be there. So let me share. You see, are you able to see what I'm sharing? Okay, so this is evolutionary computation. Yes, so I don't know whether this is large enough, but this is our case study, which we are saying, which I was presenting, and I think the book has a better, sorry, I'm going into, no. Yeah. Yeah, so I hope I have, somehow I don't have highlight text. So this is PDF and I wanted to annotate, but maybe I'll use, let me try to see if I can use this. So this is a maintenance scheduling problem. And of course, I had said that we are looking at this case study mainly because it is as a scheduling process or task, it is one of the areas where genetic algorithms have been the most successful. And it is those scheduling tasks that are really complicated and very difficult to solve. The number of techniques that are used, for example, search techniques and heuristics, but these are also challenged, okay? So here we see why these scheduling problems are difficult. They belong to NP complete problems. They're also likely to be unmanageable. They cannot be solved by search techniques, combinatorial search techniques, and also heuristics alone don't guarantee the best solution. And then secondly, they involve computation for limited resources, and so they are complicated by many constraints. So by using genetic algorithms and defining fitness functions that incorporate those constraints, there is some level of success that can be obtained. So here we are talking about sorry, I have to clear. We are talking about the specific problem that we are trying to look at. The problem is the maintenance scheduling in modern power systems. So this problem has to be carried out under several constraints and uncertainties. And here they list for us some of the problems and uncertainties. For example, there could be failures and forced outages of power equipment and delays in obtaining spare parts. Okay, so that's why we need maintenance scheduling, especially preventive maintenance. We need maintenance, but it has to be scheduled. Okay, I think I need to change the color of this drawing. Okay, I thought I can change the color, but yes. So the schedule also has to be revised on short notice. And although human experts do things by hand, there's no guarantee that they come up with optimum or near optimum schedules. Okay, so these are the challenges with maintenance scheduling, but genetic algorithms have found quite a lot of success with them. So, so we looked at the typical process involved in using a genetic algorithm or the genetic algorithm development process. So we said that we have to specify the problem, define constraints and optimum criteria. Then 2, we have to represent the problem domain as a chromosome. Then 3, define a fitness function to evaluate the chromosome's performance. Then 4, construct the genetic operators. And lastly, we run the genetic algorithms and tune the parameters. So what follows is a detailed coverage of each of those steps. So starting with step 1, that's where I was indicating that this is the most important step. because if it is not correct and complete, then a viable schedule cannot be obtained. So so we define the details of the problem all through there, that power system components are made to operate continuously through their life by means of preventive maintenance. And the purpose of maintenance scheduling is to find a sequence of outages of power units over a given period of time, usually throughout a year, such that the security of a power system is maximized. So this is something you could be doing with, I think, Umeme, or Uganda Electricity Transmission Company, or whoever generates the power, or any other power generation company. So they would need, to have these schedules. They need to monitor the power outages and prepare for schedules for maintenance before, power clients are affected. So whenever there's an outage in the power system, usually, of course, there's some loss, for example, in security. And here in security, we mean that what is secured and could be available to clients. So here the security margin is determined by the system's net reserve power, and the net reserve is in turn defined as the total installed generating capacity of a system minus the power loss due to a scheduled outage, and minus the maximum load forecast during the maintenance period. So here they describe for us, for example, that if we assume that the total installed capacity of a generator, let's say, as a power generating unit is 150 megawatts, then and then a unit of 20 megawatts is scheduled for maintenance during the period when the maximum load is predicted to be 100 megawatts, then in that case, this 100 plus the scheduled load 120 is what is being used, and therefore when we subtract 120 from the capacity of the unit, we remain with the reserve of 30. Okay, so here we are saying that maintenance scheduling must ensure that sufficient net reserve is provided for secure power supply during any maintenance period. And this one is what will define our optimum criteria. Okay, optimum criteria in this case. So here we are told that there are 7. We are told that we have 7 power units to be maintained in 4 equal intervals. Okay, so the maximum loads expected during those intervals are 80, 90, 65, and 70 megawatts. And then the unit capacities and their maintenance requirements are the ones that are represented in the table above. So this is the table that I told you in the slides had problems, because in this column, instead, we are having something different, but these are the unit numbers, like the generator numbers. If you have 7 generators that provide power or generate power, okay? So 1, 2, 3, 4, and 7. And then we are given their unit capacity. They are in megawatts. So generator 1, for example, has 20 megawatts, 2 has 15 megawatts, 3 has 35 megawatts, 4 has 40 megawatts, 5 has 15 megawatts, 6 has 15 megawatts, and 7 has 10 megawatts. So for each of these units, we are also given the number of intervals, okay? For example, number of intervals required for their maintenance. So unit 1 takes 2 intervals, unit 2 takes 2 intervals, and the rest take 1 interval each, okay? So this is the other thing we said is associated with constraints, that each unit can be maintained within either 1 interval or up to a maximum of 2 intervals. So so in this case, the constraints are clearly specified here. The constraints for the problem are that the maintenance of any unit starts at the beginning of an interval and finishes at the end of the same or adjacent interval. In other words, the maximum intervals that any unit can go through is 2. So the maintenance cannot be aborted or finished earlier than scheduled. Then the second constraint is that the net reserve of the power system must be greater than or equal to 0 at any interval. Okay, so net reserve must be greater or equal to 0. It cannot be less. Otherwise, then the customers don't get any power. So the optimum criterion here is that the net reserve must be at the maximum. We must ensure that the net reserve is at the maximum during any maintenance period. Okay, so now with that specification of the problem, having described the problem and its constraints and what is involved, then we can talk about step number 2. Step number 2 is where we have to represent, okay, represent the problem domain as a chromosome. So the case we are looking at, of course, is a scheduling case. And here we are saying that it is an ordering problem. We have to order the maintenance of the units, okay? So we are required to list the tasks in a particular order, the maintenance of the units in a particular order. So here we are saying a complete schedule may consist of a number of overlapping, for example, tasks. In other words, a complete schedule may consist of a number of, like you're maintaining a number of units at the same time, okay? So, but some of the orderings that we may think of may not be legal because they will violate the constraints that we have specified up already up there. Okay, so some of the orderings will not be legal because they may violate the constraints. So our job is to represent a complete schedule as a chromosome of a fixed length. Okay, so this is where now we have to figure out how do we represent, in our case here, how do we represent each of the tasks or the maintenance of the units as a chromosome. Okay, so we could think of a number of representation schemes. Here they tell us that an obvious coding scheme that comes to mind is to assign each unit a binary number and to let the chromosome be a sequence of those binary numbers. But they tell us that an ordering of the units in a sequence is not yet a schedule. Okay, in other words, we could say that maybe we could represent each unit as a binary number and let the chromosome be a sequence of binary numbers. So our 7 units, you know, each could be associated with a binary number 1, 2, 3, 4, 5, 6, 7. Okay, maybe unit 1 is a binary number. Unit 2 is also represented by a binary number. Unit 3 is represented by a binary number. And then unit 4 is represented by a binary number. Unit 5, a binary number. Unit 6, a binary number, like that. But we are told that this kind of representation, okay, is not yet a schedule, because the schedule tells us is associated with the intervals, and we have 4 intervals. Okay, so listing the units like that may not help. Okay, so for us, we are told that some units can be maintained simultaneously. You can have units being maintained at the same time, and we must also incorporate the time required if unit maintenance into. So we must also incorporate the time required for unit maintenance into the schedule. Okay, so in addition to having the units represented by binary numbers, we must also factor in time. Okay, if you remember the intervals, we must also talk about the intervals. Okay, so rather than ordering the units in a sequence, therefore, we might build a sequence of maintenance schedules of individual units. Okay, so the unit schedule can, in this case, be represented as a 4-bit string, where each bit is a maintenance interval. Okay, so we can have unit 1. We say that, okay, there are 4 intervals. Now here we are saying it is the 4 intervals we are going to represent as binary strings. So for unit 1, we could say that it is maintained maybe in this first interval and in the second interval, and not in the other intervals. Okay, or we could say that for unit 1, it is possible that it is also not maintained in this interval, but it's maintained in the second interval and the third interval and not this interval. Simply because unit 1 required 2 intervals according to the table. If you saw, it required 2 intervals, okay? So unit 1, if we represent the intervals as binary digits, so for unit 1, we could say that maybe it's not maintained there, but it is also maintained in the last 2 intervals. So that's why we are saying that the unit schedule can be easily represented as a 4-bit string, okay, for each unit. So if a unit is to be maintained in a particular interval, so if a unit is to be maintained in a particular interval, then the corresponding bit assumes the value 1, otherwise it is 0. So for example, here we are given that for the 4 intervals, if we have the 1 appearing there, that represents a schedule for a unit to be maintained in the second interval, okay? And it also shows that the number of intervals required for maintenance of that unit is equal to just 1, because this unit can only be maintained in that interval and it cannot be maintained in the others. So for it, the number of intervals required for it is just equal to 1. But if there was a 1 here, for example, then the number of intervals would be 2. But here it is only 1. So in the end, we can see that a complete maintenance schedule for our problem can be represented as a 28-bit chromosome, okay? In other words, therefore, for each unit, we are going to specify a 28-bit chromosome. So if I borrow some white space somewhere, sorry, I'll clear this. So we are saying that we are going to represent, so for each unit, unit 1, we shall present its maintenance schedule. And then unit 2, we shall also present its maintenance schedule like that. Unit 3, we shall present its maintenance schedule. According to the 4 intervals, unit 4, we shall present its maintenance schedule. Unit 5, we shall also present its maintenance schedule like that. And unit, this is 1, 2, 3, 4, 5, 6, also its maintenance schedule. Since we have 7 units, our chromosome here will give us the maintenance schedule for each unit, okay? For example, we may be given that for unit 1, this is unit 1, this is 2, 3, 4, 5, 6, 7. So for unit 1, we are told since it requires 2, maybe it is not maintained there, but it is maintained here in the second and third interval and not in the 4th interval, okay? And unit 2 also required 2 intervals. So we could say that maybe for it starts at the start, it goes those 2 intervals and it's not maintained elsewhere. And then unit 3, maybe it is maintained at the end. So the rest are 0 since it only requires 1 interval. Unit 4 could be maintained towards the end also. Unit 5 maybe is maintained at the start. Okay, unit 6 maybe is maintained at the second point there at the start. And unit 7, maybe it is maintained also at the end. Okay, so for each of the units, we have those 4 bits, okay, that represent their separate schedules. Okay, but when we combine them together, that is 7 times 4, we get the 28-bit chromosome. So our chromosome takes on the shape, takes on 28 bits, but each of the 4 bits will be associated with, 4 bits will be associated with each unit, okay? So, so that is the 28-bit chromosome that we can have. Now here, I'll jump this maybe and then talk about the better approach. here a better approach is to change the chromosome syntax. As probably discussed, a chromosome is a collection of elementary parts called genes. So in this case, each gene will be represented, usually is represented by one bit and cannot be broken into smaller elements. Okay, this is the usual understanding of a gene. So here we are saying for this problem, we can adopt the concept of a gene, but represent a gene by 4 bits. Okay, so now the 4 bits that we are having here, the 4 bits for each chromosome that we are having here, for each unit that we are having here, now are going to be considered as one unit. And instead of having the bits in there as genes, we are going to have all the 4 for each unit. So each unit will be represented by genes that constitute 4 bits. Okay, so here that's why we are saying that for our problem, we can represent a gene by 4 bits. In other words, the smallest indivisible part of the chromosome is a 4-bit string. So if we represent this, our chromosome, our genes as 4-bit strings, then we can perform crossover and mutation operators quite easily. It may not be a bit complicated, okay? We can perform that quite easily. So what remains then to be done is to determine what are these 4-bit genes that we can associate with each unit. Okay, what are the 4-bit genes that we can associate with each unit? So in this case, for unit 1, which required 2 maintenance intervals, then we say that we can either maintain it in the first and second interval, or we can maintain it in the second and third interval, or we can maintain it in the third and fourth interval. Okay, the rest we give the value 0. We give 0 where then it is not being maintained. So these are the genes, okay, genes for unit 1. So when we are doing mutation, for example, we could say remove this gene and get it out and flip and replace it with this other gene. Okay, so here our genes are a bit bigger. They contain more bits rather than the individual bits themselves. So likewise, we see that the genes for unit 2 are similar to those for unit 1, because for unit 2, which also requires 2 intervals, we can only maintain it either in the first and second, or in the third and fourth, or rather in the second and third, or in the third and fourth interval. So we have 3 genes for both unit 1 and 2. For the other units, the unit 3 up to 7, that require only 1, okay, only 1 interval, we are seeing that, okay, we could either maintain them at the start, or at the second interval, or at the third interval, or at the fourth interval. This is the case for all the genes that require only one interval. Okay, so now this is how we are going to represent our genes for the chromosome. Okay, so the chromosome will still be a length of 28 bits, but those 28 bits will be divided into 7 portions, 7 sections, with each section corresponding to the gene of a unit. Okay, so with this representation, then the genetic algorithm can now start creating an initial population of chromosomes by filling 7 gene chromosomes. Okay, our genes are picked from here. This is our gene pool. Okay, so for unit 1, we pick from either this or that. For unit 2, we pick from any of these 3. For unit 3, we pick from those. Unit 4, we pick from those. Unit 5, we pick from those. Unit 6, we pick from those. Unit 7, we pick from those. Okay. So so we are told that now our algorithm can create an initial population of these chromosomes by filling in the 7 gene chromosome. And they tell us the sample of such a chromosome is shown in figure 7.9. So let me clear everything here. Try to find where figure 7.9 is. So yes, figure 7.9 is here. So this is our chromosome. So you see that our genes now span 4 bits corresponding to each unit. Okay. So that is unit 4, that is unit 5, that is unit 6, that is unit 7. So what that means is that if I scroll a little bit, I'll clear this. What that means is that, for example, for unit 7, what we did, for example, unit 7, the gene we picked is the first gene you see up here. It's the first gene. It's this particular, the first gene we are using for unit 7. Whereas for unit 6, the gene we picked is the third one, okay, in that case. And then for unit 5, it is the second one, like that. Unit 4, it is the first one. And then unit 3 is should be, I think, the last one. So, so now those are our genes for the chromosome. You see that they're a bit bigger, but we are picking them from a gene pool. So in step number 3, now we define a fitness function to evaluate the performance. Sorry. Let me erase, clear all drawings. So in step number 3, we evaluate, rather we define a fitness function. Okay, we define a fitness function to evaluate the chromosome performance. So in this case, of course, evaluation is a very crucial part of the genetic algorithm, because that evaluation gives us a fitness which is the basis for mating parent chromosomes. So the fitness function must capture what makes the maintenance schedule either good or bad for the user. So in this case, this is what is important, that the maintenance schedule, we must have a way of determining whether the maintenance schedule is good or bad, okay? So here we are told that in this case, we can apply a fairly simple function concerned with constraint violations and the net reserve at each interval. So that is the aim, that we must have as much net reserves, and we must also not violate the constraints. So our fitness will be revolving around these 2 aspects. So for this particular case, the evaluation of a chromosome will start with the sum of the capacities of the units that are scheduled for maintenance at each interval. For example, for the chromosome shown in the figure 7.9, the one we've just seen, we see that interval 1 is represented by interval 1, for example, is, if we go back to, let me get this. Let me get this here. So this interval 1 is here. So for unit 1, it is not scheduled. Unit 1 has 0 in interval 1. Unit 2 has 0 in interval 1. Unit 3 has 0. Unit 4 has 1. Okay. Unit 5 has 0. Unit 6 has 0. Unit 7 has 1. So what we are doing is that for interval 1, we are trying to see what is the the sum of the capacities of the units that are scheduled for maintenance. So for unit 1, we had 0, unit 2 is 0, 3 is 0, but 4 is 1. So we multiply with the capacity of 4. 5 is 0, 6 is 0, 7 is 1. So we multiply with the capacity of 7, and this gives us a total capacity of 50. Okay, for unit 2, we see that for interval 2 rather, we see unit 1 is there, so we get its capacity. Unit 2 is not there, so it is 0. Unit 3 is 0, 4 is 0, 5 is there, so we get its capacity. So that's how first of all, we have to calculate when there's maintenance, okay, at given intervals, how much power is not available, okay? So in this case, as you see, we look at our chromosome, and then we get to see how much power is not available in each of the intervals. Okay, so for interval 1, we shall not have, for example, 50 megawatts. Interval 2, we shall not have 35 megawatts. Interval 3, we shall not have 50 megawatts. And interval 4, we shall not have 50 megawatts, okay? So now we continue to see, so this, because we want to determine the net reserves if they are sufficient enough. So we continue and we see, so these values will be subtracted from the total installed capacity of the power system, okay? So in this case, interval 1, we shall subtract, we get 50 is not there, but the total capacity is 150. So interval 1, we shall be lacking, we shall only have 100 at that point. And then interval 2, we shall have 115, interval 3, 100, and interval 4, 100. So, so we were also told that we have some maximum loads at each of the intervals, if you remember. So we also have to subtract those maximum loads. So interval 1 had 80, interval 2 had 90, interval 3, 65, interval 4, 70. So once we subtract what we got remaining here, in this case, even, you know, it reduces what is available, reduces. So this represents the reserves we are remaining with. So if we continue like that, in this case, at the end of it all, we shall get that, okay, after subtracting what is not available and also what the expected maximum load is at each of the intervals, then we get some positive numbers. So here we are saying, since all the results are positive, that particular chromosome does not violate any constraint, and that represents a legal schedule. So in this case, the chromosome's fitness is determined as the lowest of the net reserves, and the lowest is 20. Okay, so the fitness can be associated with the lowest of the net reserves in this case. So this is how you calculate the fitness of that particular chromosome up there. Okay, so for all the other chromosomes, we would follow through the same process to get their fitness. Now, if the net reserve at any interval is negative, in other words, if any of these numbers were negative, then that schedule is not legal. It violates the constraints, and the fitness function will return 0. So at the beginning of a run of the genetic algorithm, a randomly built initial population must consist of illegal schedules. In this case, the chromosome fitness values will remain unchanged, and then selection will take place in accordance with the actual fitness values. Okay, so this is I hope most of you were able to understand this discussion on how we go around the net reserves or the fitness for our chromosomes in this case. First of all, how they are represented and how we calculate the fitness. So after calculating the fitness, of course, now we go into using the genetic operators into reproduction and mutation. So here we construct genetic operators. Okay, so we determine what kind of genetic operators we are going to use. Okay, so constructing genetic operators is quite challenging practically, and in most cases you must experiment to make crossover and mutation work correctly. So in this case, the chromosome has to be broken up in a way that is legal for our problem. Now, you realize that we have represented our chromosome a bit differently. The genes have more bits. So when we talk about crossover, it's not like you're going to flip a single bit. This time you're going to exchange, for example, the whole gene, okay? So in this case, each gene in a chromosome is represented by a 4-bit indivisible string. It cannot be divided. So that that puts a limit on the number of on the kind of operations we can perform on the kind of crossover and mutation operations we can perform. Okay, so the diagrams here now illustrate how, for example, the crossover operations will look like. So we have the same approach that in crossover, we use a crossover probability, PC. We select a breakpoint. For example, in this case, it is here. And now we exchange the parts that come after. So if this is parent 1, and this is parent 2, and this is the breakpoint, then what is up here comes down, and what is down here goes up, okay? So with that, when we do that, we end up with these children chromosomes, okay? So you see that what was up here in its entirety was brought down. That's why we have 0, 1 here, because 0, 1 is here. So we have 0, 1 here. And what was down is brought up. That's why we have 0, 0, which we had here, okay? So these are the resulting children. So this is how crossover works in this case. Now, mutation is not like you change only 1 bit. Instead, you get the whole gene and you replace it with another gene from the gene pool. So for the third unit, okay, this is the third unit. It had like four genes to work with or to exchange. So you can pick one of those and put them here. So here, we removed the gene with where the third unit was maintained at the second interval, and we replaced it with the gene where the third unit is maintained at the last interval. So that is how mutation works in this case. Okay. So then lastly, in number 5, we can run the genetic algorithm and its parameters. Okay. So of course, when running the genetic algorithm, we decide on the population size and then the number of generations. Here, there's some discussion about some of these figures, but now I think it is safer for me to stop here and I go back to the slides. Let me share the slides now. Okay, I hope the slide is showing. So when we run, here we are being told now that we can decide on the population. Let me see. Yes, we can decide on the population size. Also, these crossover and mutation probabilities are there. And then, and also the generations, how many generations we want to run for. Okay, so here in this run, where we have a population of 20 chromosomes, we get, this is what we have down here is the schedule, the best schedule that was returned, that in the first interval, we maintain unit 4 and 5. And then in the second, we maintain unit 2 and 7. And then in the third, we maintain unit 2, 1 and 6. And in the fourth, we maintain unit 1 and 3. So that is the schedule, okay? So in this schedule, we have, this is the maximum load in each of the intervals that is expected. And what we have here is the capacity of each unit. So unit 4, what we have here is the generator capacity, for example, if unit 4 is a generator, and unit 5, we also have its capacity there, okay? So this is what is not available from the units when they are being maintained. And this is the maximum load when the power system is working, and what is left in white is the reserve. Okay, so now so here after 50 generations, this is what we get as the best schedule, and we can continue with more settings. So here in this case we increase the number of generations. Okay, we increase them to 100. So here it's the only change we did was to increase the number of generations. So we come up with a different schedule. If you compare the schedule here with the schedule here, it is a bit different. So in this case, we have that we maintain unit 1 and 7, 1 and 2, 2, 3 and 6, and then 4 and 5, okay, with these net reserves. So maybe the net reserves here are much better than what we had previously here. You never know. And then as we continue, in this other case, previously we were, in this other case now we changed the population size. Previously we were working with a population of 20, but now we change the population size. Okay, so we use 100, the other parameters are the same. The mutation rate is also still, mutation rate is the same. So in this case, you see that the schedule is different. If you compare to what we have had previously, the resulting schedule is different, okay? In interval 1 is unit 3, interval 2 is 1, 2, interval 3 is 1, 2, 5, and 7, and interval 4 is that. And we can continue. Now here we change the mutation rate. We have 100, a population of 100, and we do 100 generations, okay? So when we change the mutation rate, we even get a different schedule as indicated in this case. Okay, so that brings us to the end of this topic. I really have talked through them. I've taken a longer time, I think, with your class because I went to the book to explain, but I think it is good that I went through it. So it brings us to the end of the topic and also the end of the lectures. I should have finished last week, but I'm very glad that you allowed me to finish today. Then I don't come back to you at on Friday or even Saturday to disturb you. Rather, you'll be doing your tests, which should be like more of a practice session for you in preparation for your exam as well. So that's where we end today. The scope of the test is where we, somebody requested me not to bring these genetic algorithms in the test. So I don't know whether they will come. But where we stopped with the first test, okay, that point of either the bias or the certainty factors coming forward, that's where we shall start from. So we shall not do in the second test, we are not going to do, in this other test, we are not going to do what we did in the first test. What we did in the first test now may come back in the exams, but not in this other test of either Friday or Saturday. So I hope that is clear. There are definitely previous papers, but most of them are obsolete, I think, now with the topics I cover. So what I covered today, for example, I didn't cover it last year, and I never said anything about it last year. But yes, the questions will come from what has been covered in class. In most cases, they are not going to come from anywhere else. So there are some question papers as well, I think. I need to look around, but usually it's safer. It's safer The marking guides are in these slides themselves. Most of the questions come from the slides. So you'll find that the marking guides are there. So I could tell you, for example, to say give such a case study, and I tell you to describe or demonstrate the use of the genetic algorithm. So if you discuss the steps the way I've covered them today, then you get your marks. That's but I'm very sure that most of you will pass very well, especially after doing the second test. You'll pass very well when you get to the exam. So let me stop here for today. Let's meet on Friday, I think. Friday around 4 or 5 for the test. If not Friday, then we'll end up in Saturday, but most likely Friday.